Hello, Jai Sundara.
Yes, sir.
Jai Sundara, can you share a message to others that I am going to start the lecture soon? Because only you are available. So if there are maybe two others persons, then I can start the lecture. So if possible, please share a message to others. Madhushani, I am waiting till the other persons join. I will wait for one other person and I will start the lecture. Please share the message to your friends that the lecture will be started very soon. Okay, I think it's time to start, um, Madhushani and Jai Sundara. So we will start, and actually, what I what I am going to do today, I need to give you a kind of flashback memory of the things we discussed in our last lecture. That is the settlement of soil. Actually, first I will have a summarize, maybe around 5 minutes time. I will be discussing the major points of last week, and after that, I thought to have a session for the activities, some of the problems, because as I said last time, um, I already included one question from this topic. So it's very much important for you to understand and get used to these examples. Then only I think you will be able to answer the questions in a proper manner, right? So that's why I thought to give you a kind of flashback session of the things we discussed last week. And also, based on the theories, we will be discussing some of the good examples so that you will be having a good exposure for the exam paper. So, as I said, I repeat, there will be one question from this topic. So it's better if you have a kind of thorough knowledge regarding the theories and all the and also the work examples, right? So, as I said last time, soil settlement is a kind of major problem in civil engineering industry, and we explained the settlement can be computed in three categories. First, we said the immediate settlement. We said using the elastic theory, we can determine what's the amount of immediate settlement. Then we say there is primary consolidation settlement and also secondary consolidation settlement. Under the primary consolidation settlement, we discuss, okay, we can use the consolidation theory, and secondary consolidation, actually it's depend on the creep and kind of plastic deformation of soil. So we discuss all those things, and we said in terms of the settlement, primary consolidation settlement is the major concern, because as you can remember, mm, if we plot the settlement versus time, you can see the immediate settlement is kind of comparatively low value, and it will not take much time, and the magnitude is also very limited. But when it comes to the consolidation settlement, you can see the amount, the magnitude is also high, and also it will take huge time to have the final consolidation settlement. So when it comes to the secondary consolidation settlement, you can see the magnitude is very much less. So when we talk about the settlement, the primary consolidation settlement plays a major role in settlement in terms of the magnitude and the time. So that's why we are much worrying about this consolidation settlement. We say we have to use the consolidation theory to evaluate the magnitude and the time required for the consolidation settlement. Hope you can remember the things we discussed last time, right? So if I move into the consolidation settlement, I said actually the consolidation settlement is taken place due to the expulsion of water, right? As I said you last time, the soil is having an internal structure so that there are soil particles. In between the solid soil particles, there are certain voids. These voids in saturated situation are filled with water, right? So when we compress or when we apply an external load, what will happen is the entire soil body will be compressed, right? So the entire soil body compressed means the total soil body, the compression will take place, right? But when we check the soil behavior, we observe that first the pressure, the additional pressure will be taken by water, right? So as you know, if a kind of water body is pressurized, what will happen? Water tries to flow away. Water tries to release its additional pressure. The same theory applies here. So what happens is when you create certain foundation, water will take that additional loading. But even though water takes the additional loading at first, it tries to release that pressure, right? So when we talk about the granular soil, like sandy soil or gravelly soil or whatever kind of uh, coarse grain soil, the problem is not that big, because the voids are interconnected, the water pathways are clear. So once you pressurize the soil body, water will be pressurized, but the pressurized water, it has clear pathways to release its additional pressure. But when it comes to the fine grained soil, like clay, what will happen? These water pathways are blocked because the particle size of the soil is very limited, very small. So as a result, what happens is when you apply certain additional pressure on the soil body, the water will be compressed, but it cannot release that pressure, right? So it will take time to release the pressure because the water pathways are blocked, right? So what happens now, the releasement of water will take place over a long period, sometimes years, sometimes maybe 100 years, maybe more than 100 years. That depend on the soil type and soil internal structure, right? Now, that's the reason, right? These water pathways are not interconnected and it will take time to dissipate the pore water pressure, right? As a result, this dissipation will take place for a longer period. So as you know, once the water is removed, let's say after 10 years time, if the water is removed, that space become void, so that the settlement will taken place, right? So that's the procedure. So since this takes for the clay type soil, this will take around 100 years sometimes 50 years, sometimes 10 years, right? So that depends on the soil type and soil internal structure, right? So that's the problem. That's why we say the consolidation settlement is a problem, because it will take huge time to complete and also the magnitude is too much high sometimes, right? So hope you understood, and we said the mechanism. We simulated this mechanism through spring cylinder model. I am not going to discuss about this thing because we discussed this thing in detail last time, right? So I said when it comes to the settlement, two major things are very much important to understand. The first thing is the magnitude. The second thing is the rate. Magnitude means what is the amount of settlement? Sometimes 500 millimeters, sometimes 700 millimeters. So, kind of what is the amount of settlement? So, we have to determine as civil engineers, once you create certain building, what is the amount of settlement? That would be the magnitude. And the other thing we are interested in is the rate, right? Rate means the speed. How long will it take? Maybe years, maybe months, right? So that is speed or the time duration, right? So two things we need to know. So we discussed last time how to determine this magnitude and rate. So let me explain you once again. Let me remind you, this is the equation we have used for the time or the rate, right? T is the time required for certain degree of consolidation. Capital T is the time factor. H is the length of drainage path. CV is the coefficient of consolidation. When it comes to this time factor, we say that is a kind of constant. So that constant can be determined by using two different equations depending on the degree of consolidation you are considering, right? So in case your degree of consolidation is less than 60%, you can use this equation. In case your degree of consolidation is more than 60%, you can use this equation. So that you can evaluate the time factor relevant to your case and just substitute here. So I discussed with you last time how to determine the drainage pathway, and CV is normally given in the question, right? So that you can evaluate the time required for consolidation for the considered degree of consolidation, right? So then I said the magnitude. The magnitude was determined based on the pre-consolidation pressure, right? Hope you remember what is defined as pre-consolidation pressure. So in simple words, the pre-consolidation pressure would be the maximum pressure the soil experience in its history, right? In its history, what is the maximum pressure, right? So that would be the uh, pre-consolidation pressure, right? So this one, sigma dash P. right? So depending on this pre-consolidation pressure of a given soil, we can determine whether the soil is over-consolidated or normally consolidated. Okay. So we will see some of the examples. Last time I explained this one. So in that situation, if your soil is over-consolidated, you have to use CR, recompression index, in order to determine the magnitude of the settlement. In case your stress condition is normally consolidated situation, in that situation you have to use CC, right? So depending on the situation, we said there are three cases. The case one would be if your soil is normally consolidated, this is how you have to determine the soil settlement. Okay, the magnitude. And if your soil is over consolidated, you have to use this equation to determine the settlement, right? In case your soil is over consolidated, but when it is compressed, it is becoming normally consolidated. In that situation, you have to use this equation where the combined situation is there, right? So that you can determine the settlement. So this is the summary. So the time can be determined by using this equation. For normally consolidated clay, the settlement can be computed by using this equation. For over-consolidated clay situation, you have to use this equation where the combined situation is there. That means first, before the foundation is to be constructed, the soil will be over-consolidated. Once the loading is applied, the soil will be the normally consolidated. In that situation, you have to use this equation to determine the settlement magnitude, right? That's how you have to evaluate the time and the amount of the settlement, right? So it is not much kind of big issue. Very simple equations are there. You have to understand how to apply these equations. So your question, exam paper question, is solely based on these three and four equations, right? So every equation relevant to the question will be given in your exam paper. Don't worry, right? It will be there in your exam paper. So I will mention each and every um, equation which is required for the uh, question, right? So you may use those equations, you may refer to those equations, and based on the equation, you have to evaluate what is the answer, right? What you want to know is how to understand the practical situation which is given in the question and how to relate that question to these equation and how to use the correct, how to understand the correct terms and how to use this equation to evaluate the unknowns. That's what you are requested to do, right, during the exam paper, right? So then I say elastic settlement. It is a kind of empirical correlations and tables are there. So you may use these equations and you can determine the settlement. And then I say the secondary consolidation settlement can be determined by this. Anyway, I didn't focus much on the immediate settlement and the secondary consolidation settlement. The reasons actually uh, when you compare the primary consolidation settlement, elastic settlement, and secondary consolidation settlement. The primary consolidation settlement plays a major role. So you worry about the primary consolidation settlement. When it comes to the secondary consolidation settlement and elastic settlement, the amount will not be that much, right? Okay. So with that, we will actually, I rushed over the slideshow, right? So this is 3 hour lecture, right? This consolidation, the settlement. Anyway, I tried to give you a kind of brief review on the things we discussed last time. So this is where we are going to start today, right? So I'm going to start from this slide onwards. So we will be discussing some of the practical examples. So give you, I recommend you to have, so try to work these examples by your own so that you can get a certain kind of exposure before you go to the exam, right? So I recommend you to work alone on these questions and have a kind of understanding, better understand. Once you do only, you can understand these things, right? So I don't know, maybe in your previous studies like HND, NCT, in whichever course you were in, you may come across these kind of questions like settlement, consolidation, etc., etc. But it's better if if you have a kind of piece of paper and work on this one with me, right? So that you can understand the theories well, right? Okay, the problem number one, find the settlement due to consolidation of a 3 meter by 3 meter column foundation with a load of 200 kilonewton. The foundation is placed 1 meter below the top surface and the clay layer is 9 meter thick. There is a sand layer underneath the clay layer. The density of the clay layer is 18 kilonewton per cubic meter and the compression index CC of the clay layer is 0.32 and initial void ratio E naught of clay is 0.80. Assume that the pressure is distributed at 2 to 1 ratio and the clay is normally consolidated, right? What you have to do is you have to determine the final settlement due to consolidation. So can you, after reading this problem, can you make a sketch, right? So that you can understand the arrangement of the soil layers, right? Can you do that? So I will give you 2-3 minutes. Read a kind of this question and make a sketch on the soil arrangement, right? We'll give you 3 minutes. Try to work on that. If somebody made a sketch, please share through the chat box if possible, so that I can understand whether you are following me or not. Okay. Anybody? Jayasundara, were you able to work on that? ඇන්දද ජයසුන්දර මදුෂානි ස්කෙච් එක කරන්න පුළුවන් වුණාද? පොඩි දෙයක් තියෙනනේ. මොකද උනේ ජයසුන්දර මදුෂානි? හ්ම්? ඕකේ. බලමු අපි. මොකද මේ කියන්නේ? First, the foundation is placed 1 meter below the top surface, right? So the foundation dimensions are given. The plan dimensions are 3 meter by 3 meter. And the foundation is placed 1 meter below the top surface, right? So the ground level is there. From there, 1 meter below, you will be having your foundation. The plan dimensions are 3 meter by 3 meter, okay? And clay layer is 9 meter thick. So there's a clay layer. So it will be 9 meter thick. A sand layer beneath, underneath the clay layer. Sand layer is there, which is underneath the clay layer. Yes. Okay, Madhushan. I'm just seeing your one. Yes. Good. Right. Okay. I really glad to see these kind of responses because as you know, this is online session. So really like to have the responses from students. Then only we feel like, okay, you are doing something with me, right? You are listening to me. So it's a great satisfaction to every lecturer. So I really like if somebody answer or if somebody respond when the online session is going on, right? So thank you, Madhushani. So okay, now this is what I mentioned. Okay, the kind of footing is there. The footing dimensions are 3 meter. The lateral dimension also 3 meter. So from ground level, there will be 1 meter down to the base of the footing. And the clay layer will be there for 9 meters. You can see from ground level to the bottom of the clay layer, it will be totally 9 meters, right? So after that, there will be a sand, right? So this is what I requested from you to draw. So very correct, Madhushani. So, but what you have to do is you have to mark the footing as well, right? So the footing you mark, the reason, here something special is there. The density of the clay layer, you have to mark as 18 kilonewton per cubic meter like this. And also the compression index CC is given as 0.32. And initial void ratio E naught is given as 0.8. So whatever the information given in the question, you better mark in the sketch. And the other thing here, assume that the pressure is distributed at 2 to 1 ratio. Hope you can remember. We have been discussing this theory when we discuss about the stresses inside soil, right? So maybe 3 weeks before 3 4 weeks before uh, we discuss about the topic called stresses in soil. So there we discuss there are many methods available to evaluate the stresses within the soil. One of such method is the approximate method. So approximate method, we use 2 to 1 method for the for evaluation of the distributed pressure inside soil, right? So the 2 to 1 method means if you go uh, vertically 2 meters down, horizontally you have to go 1 meter. So that's how the pressure is distributed. So this pressure here, certain pressure is applied. That pressure will be distributed through the soil so that it will be distributed in 2 to 1. 2 to 1 means vertically if you go down 2 meters, horizontally the distribution will be 1 meter, right? So that's what the 2 to 1 method is. One more important thing, when the clay layer is given, right, you have to always consider the mid layer of clay, the mid depth. So the settlement computations, the duration computation will be done at the mid layer. So that is a kind of convention, right? So here the mid depth would be from the foundation to the layer, right? What's the depth from the foundation bottom to the layer end? It will be 8 meters. So you have to mark the mid depth from the bottom of the foundation. That's why it is somewhere here. So the total depth would be 9 meter. In that situation, we have to go for 4.5. But the stresses will be calculated after the footing depth. Okay. So footing here at 1 meter, the balance depth would be totally 8 meters. So you have to divide by 2. That would be the mid depth of the clay layer. Okay. So those are the very important things, right? So one more thing. Now from here to here, the distance would be 4 meter. You can see my mouse pointer. So altogether the depth would be 4 meters, right? So if the stress distribution is 2 to 1, right? 2 vertically, 1 horizontally. In that situation, if you go 4 meters down, the distribution will be 2 meters in each side. Here also 2 meter, here also 2 meter. That would be the distributed area. Not only this direction, but also the lateral direction also it would be the same, right? So now here, this dimension remains as it is, here 3 meter. So it will be remain as it is as 3 meter. So distributed length would be 2 meter this side, 2 meter this side. Okay. Hope you understood. Right? So with that understanding, first what you have to do is you have to now this is the equation. Hope you can remember. So in the question, it is clearly mentioned that the soil is normally consolidated, right? Soil is normally consolidated. That is clearly mentioned. So in situations where the normally consolidated soil are available, this is the equation to compute the settlement of the soil. Okay. So delta H would be the total settlement. H is the thickness of the compressible clay layer, and Cc is the compression index, E naught is the initial void ratio, P naught dash is the initial stress, and delta P would be the additional stress created by the foundation. Okay. So with that understanding, we will substitute the correct values. So what would be the H? Here, clay layer is 9 meter thick, but the footing is placed 1 meter below the surface. So top 1 meter is not subjected to consolidation. Why? What's the reason? You can see the stresses are applied from there onwards, right? From the footing bottom onwards, your stresses will be generated. Means top 1 meter, there will no any additional stress, no impact. So because of that thing, we will not consider the top 1 meter. So the layer thickness was given as totally 8 meters, right? So that's why a clay layer thickness of 8 meter below the footing is subjected to consider, right? So in order to find the effective stress, how to determine the effective stress at the mid depth of the clay layer? Very easy. So initial weight, totally, the gamma would be 18 kilonewton per cubic meter, right? So 18 into what would be the initial stress at the mid depth? Total depth would be 5 meter, right? Total clay layer thickness is 5 meter. So you have to get that weight. That would be the initial stress. Before the foundation is applied, the initial stress at the mid depth of the clay, right? So in the situation, what is the weight coming due to the soil weight, right? So that would be 18 into 5. Totally, it will be 90 kilonewton per square meter, right? So then you have to calculate what is the increment of the stress due to the footing, right? So how to evaluate that one? So total load is 100 kilonewton. It is given in the question here. Uh, Total load is, foundation load is 200 kilonewton. Sorry. Here 200 kilonewton, not 100. Actually, it should be 200. It should be corrected here. It should be 200. Is distributed at the large area at midsection of the clay layer. So area of the midsection of the clay layer, how to do? Very easy. Here, what is the area? 3, 2, 2. All together, 3 plus 2, 5. 5 plus 2, 7. So the lateral dimension also same, because the foundation is 3 by 3. Lateral dimension also same. So totally 7 by 7, 49 square meters. So additional pressure due to the foundation would be 200 is the point load divided by this increased area, that would be 49. So additional pressure would be 4.1 kilonewton per square meter. Is there any problem up to now? If there's any problem, please let me know. Any problem, Abhishani? If you are okay, we will proceed. If there's any problem, please let me know, because this kind of problem will be available in your exam paper. Now, what we have did here, so before the application of this 14, the soil will be there, right? So we calculate the initial stress due to the soil load. So in that situation, we have to go for the full depth, 5 meter. That's why 5 into 18. 18 is the unit weight. So that 90 kilonewton per square meter. So that would be the initial stress. So as a result of foundation, now 200 kilonewton is applied here. So contact pressure would be 200 divided by 3 divided by 3. Okay. Now contact area would be 3 by 3. That would be 9 square meter. 200 divided by 9 square meter will be the stress at this point. But we are considering here at the mid layer of the clay. So when we talk about the mid layer, the stress will be distributed at the mid layer. How will be the distribution? 2 to 1. It is there in the question, right? So when 2 meters down, horizontally you have to go 1 meter. Now here altogether is 4 meter. If 2, there will be 1, then 4 means 2 meters, right? Here will be 2 meters. Here also 2 meters. So the distributed area will be 2 plus 3 plus 2, that would be 7. The laterally also there will be 7 meters, right? So think about 3D situation, then you will understand. So now the load will be distributed in this enlarged area. 200 divided by 9 by 9. So, sorry, 200 divided by 7 by 7. Here 7, no? 2 plus 3, 5. 5 plus 2, 7. Right? 7 by 7, that would be 49. That's why we divided by 49 here. 200 divided by 49. So, this will be the additional pressure. Now, in this equation, you know P naught dash, the initial stress. Initial stress is 90. Okay. Here also initial stress, that would also be 90. Delta P is the additional pressure due to the foundation. So you calculated that as 4.1. Now we have to apply Cc. It is given in the question. E naught, it is also given in the question. H, the thickness of the clay layer for consolidation settlement. That will be 4 meters. Here 4 plus 4. Here 4 plus 4. That would be the thickness of the clay layer. Totally it is 8 meters. So now you can substitute the correct values here. 8 into 0.32, E naught is 0.8, P naught you calculated as 90, delta P you calculated as 4.1, P naught you calculated as 90. So finally you can have this value. So meters 0.0275. In other words, right, 27.5 millimeter. 27.5 millimeter. That would be your answer. So hope it is clear to you, because nobody is talking to me. I hope there are no problems or confusions available with you, right? Okay. We will move to the second question. Consider the soil profile shown in the following figure. The soil is subjected to an uniformly distributed load delta sigma 31.1 kilonewton per square meter on the ground surface. The sand is such that gamma D is equal 16.5 kilonewton per cubic meter and gamma set sand 19.3 kilonewton per cubic meter. Underlying clay gamma set clay is equal to 20.5 and liquid limit is 38. E naught is 0.89 and CS is equal to 0.25 cc. Depths H1, H2 and H3 are as shown. Determine the primary consolidation displacement of normally consolidated clay layer, right? So now this is the soil profile. You can see. Here the sand layer is there. Here you can see a rock, right? So clay layer is there. The thickness is 4 meter. Groundwater level is somewhere here. You can see from the top of the soil layer to the groundwater depth. The depth would be 2 meter, and the saturated sand would be 3 meter deep, and clay is 4 meter thick, and then there will be a rock, right? So all the information is given to you in the question. So what you have to do is, once you apply certain additional pressure, distributed load of 31.1 kilonewton per square meter on the ground surface, what would be the primary consolidation settlement, right? So that is the question asked to you, right? So gamma D, everything is given to you. So let me explain this example, right? So in situ overburden pressure. So first what you have to do is you have to, now this is the equation, no? The same equation, right? First you have to evaluate the initial stress, then the additional stress, right? And then you have to evaluate CC and E naught, right? So now let's see. First you are now evaluating the in effective stress at the mid depth of the clay layer, right? So now here first you have dry sand here. In the dry sand you can see the um, gamma value has been given as 16.5 kilonewton per cubic meter, right? Then we have gamma set sand, means saturated sand over there. Here, dry sand is available. Here, saturated sand is available. In the dry sand, you have to apply gamma dry. In the saturated sand, you have to apply gamma sand, right, of the sand. Every value is there in the question. Here 16.5, here 19.3. And also underlying clay, gamma set of clay has been given as 20.5. So with these values, we will calculate the initial overburden soil pressure. Gamma D sand 16.5, and you have to multiply the relevant depth. Relevant depth is 2 meter, right? And then we have gamma set sand minus, because we are calculating the effective stress, you have to deduct the pore water pressure. Here 19.3 is the gamma set sand. So 19.3 into 3 minus 9.81 into 3. So 9.81 is the, or 9.8 is the gamma W, right? So what I have done is gamma set sand minus gamma W into relevant depth. So very clear, no? And the other thing, same thing, gamma set clay minus gamma W, because this is also saturated. So in that situation, you are now evaluating the effective stress. So in that situation, you are considering mid depth of the clay layer. So gamma value of the clay, it is given in the question as 20.5. 20.5 minus 9.8, that would be the effective stress portion, into 2 meters. Why? Here the mid depth would be 2 meters. So that's why 4 divided by 2 here. So the totally, the initial stress has been here mentioned as 82.9 kilopascal, right? Hope that is clear to you. Now, you know sigma naught dash. Also, you know, in the question it is clearly mentioned, uniformly distributed load has been applied. So the foundation loading is given as 31.1. Now the final load also you know. In this equation, you know sigma naught dash. Now you calculated as 82.9. Delta sigma also it is given in the question. Again sigma naught dash is here. And then we have CC. CC it is given in the question, correct? No. CC is not given in the question. Then how to evaluate the CC value? Compression index. Here, liquid limit is given as 38. If liquid limit is given as 38, you have an equation, right? This equation. You can use this equation and evaluate the CC value. 0.009 liquid limit minus 10. So that you can evaluate the CC value, right? So you apply that evaluated value here. E naught it is given in the question, 0.89. So now just a matter of correct substitution of correct values. So CC value, you evaluated as 0.252. You just substitute here. H, the height of the clay layer to be consolidated, it is 4 meter, right? And then 1 plus E naught is 0.89 log 10, 82.9. You evaluated this one, the delta sigma, it is given in the question. Again, sigma naught dash, right? You just apply, you can see the settlement is 73.8 millimeters. Hope that is clear to you. Okay. Now, in the above soil problem, given the coefficient of consolidation CV as 0.24 centimeter square per second, how long will it take for 75% consolidation to be over in the field? What's the time required? First, your equation would be this one, right? Your equation would be this one. So sorry, Madhushani. Can you all hear me? Okay.
Yes.
Okay. Okay, Madhushani. Now, um, actually, now I hope you remember this one. This TV, there are two equations, right? Hope you can remember. Let me show you once again. So, this T value, capital T value, there are two equations depending on the rate of consolidation. In case of rate of consolidation is 60% or less than 60%, you have to use this equation. In case the rate of consolidation is more than 60%, you have to use this equation. Okay. So now in our question, our consolidation is 75%, right? So that's the reason we use this equation. The log equation we use, the reason is that. Okay. So now here, so we apply our rate of consolidation given in the question 75%, no? So that's why we apply this equation 75. Now this is calculated as 0.477. So that's why here we applied the same value. Now here one information. Now CV also given in the question. No issue. You can refer to the question and you can have that value. It is there in the question. Okay. And only the problem is H. Now I want to know your knowledge about this H. Here H is not the thickness. H is the length of the drainage path. Length of the drainage path. Now the drainage path, the definition is the shortest length of the shortest length of the water droplet to remove its additional pressure. the shortest perpendicular length, or I may say the longest perpendicular length of a water droplet which runs to release its pressure. එයාගේ additional pressure එක අයින් කරන්න වතුර බිඳුවකට යන්න අවශ්‍ය දිගම length එක තමයි අපි කියන්නේ drainage pathway කියලා. Okay. So in this situation, let's say your top layer is sand here, bottom layer also sand here. This is like a sandwich layer, right? So in a sandwich layer, what would be the drainage pathway length, right? I said the longest run of a water droplet in a perpendicular pathway to release its pressure. So that would be here, no? Now water here can perpendicular run, it can go like this. Water tries to escape, no? Water will not go from here. Water definitely find its shortest pathway, right? So water droplet here, it will go this side. Water droplet here, it will go downside. So what would be the maximum length then? A water droplet at center, it has to run from here or the other direction. Whichever direction it can transfer. Both ways it can go through. So what would be the drainage pathway length? Capital H here. That would be thickness of the clay layer divided by 2. Understood? Thickness of the clay layer divided by 2. So in case of a soil layer where top and bottom you have certain barriers, like let's see, you have a rock layer here. Okay, rock layer. So rock will not permit water to pass through, right? Here also you have a rock layer. Now clay layer is sandwiched in between the two rock layers, right? So in this situation, let's say here this is a sand layer, not rock layer. This is a sand layer. So in that situation, what would be? Now here you have rock layer, here sand layer. In this situation, what would be the length of drainage pathway? So water here has to go here. Water here has to anyway go to here, because downside we cannot expect the water to dissipate, right? Here also it has to go to here. So what would be the maximum length then? From here to here. Water droplet here, it should anyway go to the top until it releases the pressure. So the drainage pathway here, it would be the thickness of the clay layer. So you have to always think about the drainage arrangement, whether it is a doubly drainage or singly drainage. If it is singly drainage like this, the drainage pathway would be the total full thickness. If it is singly drained, full thickness. If it is doubly drained, you have to divide the drainage, the thickness by 2, right? So here, what happened? Now H should be substituted here. So how about this H value? You can see here we have rock layer. Here we have a sand layer. So it is like singly drained situation. So full depth, the water droplet has to pass through to release its pressure, right? So that's why we have to apply 400 here as drainage pathway. Now everything is applied in centimeters because CV value is given as centimeters. Here you can see centimeters. So that's why 4 meters in order to convert in centimeter, 400 it should be. So the t value, the time would be this. So when you convert into days, it would be 221 days. 221 days. Okay. So now it is clear to you, Madhushanani. You are the only person available today, right? Okay. Shall we continue, Madhushani? Or
Yes,
else
sir.
I can share you the presentation you can refer to. If you want my clarification, I can continue the session because only you are available. So if you want to continue, I can continue, no issue. If not, we will wind up the session and we will have a kind of session tomorrow. Tomorrow also we will be having a lecture. So since you are only available, if you are okay, I can continue. If not, we can wind up the session. I can share the presentation with you. You can refer to this and you can have certain understanding. It's up to you, Madhushani. මොකද කරන්නේ?
අපි කන්ටිනියු කරමු සර්.
අපි continue කරමු. Okay. Okay. So then, Madhushani, I prefer to discuss this question next because my exam paper question is more or less similar to this one, right? So I first discuss on this question and after that we will wind up the session. Okay, Madhushani, right? So Madhushani, we will have 10 minutes break now. After that we will come back to the session and we will be discussing this question. After that we will wind up the session, right?
ఓకే సార్.
Okay, Madhushani. So have 10-minute break and come back to the session, please. Okay, Madhushani. We will continue, right? So, so this is the question. So, which is more, most similar to your question paper. Ignore the immediate settlement and calculate total consolidation settlement of soil profile composed of two different types of clay, i.e. clay 1 and clay 2, due to 150 kilopascal net foundation load. Take unit weight of water as 10 kilonewton per cubic meter, right? So here what happened is there is a foundation, right? So as a result of this foundation, a 10 meter by 10 meter foundation, there will be a uh, foundation load 150 kilopascal, right? So the foundation is located 2 meters down the first clay layer, and the groundwater table is located at the same depth. Okay. So the clay layer 1, the properties are given. Clay layer 2 also properties are given. What you have to calculate is consolidation settlement of clay layer 1 and clay layer 2. So both layers are clay layers, but the properties are different. Unit weight, um, somewhat different. And then we have CR value, CC value, so E naught value, pre-consolidation pressure. So everything is different, right? So that's why, uh, since it has distinct two properties, right? Two set of properties, we say there are two layers of clay, different types of clays are available, right? So the first layer, it is altogether 8 meter deep, and clay layer 2, 6 meter deep. But the consolidation will be taken place only in 6 meter, first 6 meter of the clay layer 1. This 2 meter, no consolidation will be taken place because the foundation will be started at 2 meters down the ground level. Okay, right. So with that understanding, we will proceed. Here, what are the properties given? Pre-compression index is given, CR. Also, uh, consolidation rate, this coefficient of consolidation is also given as 0.15. Initial void ratio is given, and pre-consolidation pressure is also given as 80 kilopascal. So the second layer also similar properties have been given. So you can see the pre-consolidation pressure in clay layer 2 is 200 kilopascal. Why this pre-consolidation pressure is given to you is to determine whether the clay is normally consolidated clay or over consolidated clay. If the current pressure, if the current pressure is higher than pre-consolidation pressure, you can say the clay is normally consolidated clay. I repeat, if the current pressure is more than the pre-consolidation pressure or equal to the pre-consolidation pressure, you can say the soil is normally consolidated. If the current stress is less than the pre-consolidation pressure, you can say the clay is over-consolidated clay, right? So hope you understand. අතීතයේ සොයිල් එකට බලපාපු වැඩිම ස්ට්‍රෙස් එක තමයි මේ pre-consolidation pressure කියලා කියන්නේ. ඒක 80යි. හිතන්නකො දැන් ප්‍රෙෂර් එක ඊට වඩා ගොඩක් වැඩි හෝ ඒකට සමානයි කියලා. ඒ කියන්නේ මොකද්ද වෙන්නේ? අතීතයකට වඩා දැන් වැඩි. ඒ කියන්නේ මේක normally consolidated clay. අතීතයක වැඩි නම් දැන් ප්‍රෙෂර් එකට වඩා. ඒ කියන්නේ අතීතයේ යා වැඩිපුර ප්‍රෙෂර් එකකට ලක් වෙලා. ඒ කියන්නේ මෙයා over consolidated clay එක. Okay? Understood? Right. So with that understanding, we will proceed. Now, settlement will take place due to the loading applied at a depth of 2 meters. Thus, all consolidation settlement calculation will be performed for clay soil beneath the foundation, right? So, consolidation will take place on this layer only. This portion we will not consider because the foundation loading is applied somewhere here. Okay. Reminder, general equation of 1D consolidation settlement. One-dimensional vertical consolidation for over-consolidated clay. Sorry. Here, I have mentioned here the combined situation, right? I mentioned in the presentation with today in the beginning, there are three cases. For normally consolidated clay, there's one set of equation. The over-consolidated clay, there is one set of equation. But in case of combined situation where the soil is firstly over-consolidated, and then once the load is applied, it will be subjected to normal consolidation situation. In that situation, you have to use this combined situation. So we have to always use the mid depth, right? Because now in this situation, right, here the consolidation will be taken place from there onwards, right? From here onwards, the consolidation will be taken place. So the mid depth of the clay layer number one first we will consider. So clay layer number one mid depth will be somewhere here. So it will be 3 meters down there, right? 3 meters. So when you calculate the consolidation settlement of clay layer 2, you have to consider the mid depth somewhere here. So from here to here, it will be totally 9 meters. So you have to consider 9 meters there. Hope you understood, right? So always you have to consider the mid depth, right? So clay layer number one, initial effective stress. So you have to consider whatever the soil layers above the clay layer number one and calculate this one. Here we have now initial condition, the foundation loading is not there. Whatever the stress coming is from here to here, the total depth. But here you can see this layer, this part of the clay layer is unsaturated. Here, this part of the clay layer, it is saturated. So you have to use gamma dry situation for this one and gamma sat for this one. Okay, that's what I did here. 2 into 19. Here, no pore water pressure is there. Why? Here, gamma dry situation is there, no water is there, so pore water pressure not available. But here what happened is, this portion, it is fully saturated, so that here we have to, now depth is 3 meter, why mid depth is there, 3 meter, and then gamma set is 20, this is gamma set, no? So you have to get the gamma dash set. So gamma dash set would be 20 minus, this is pore water, sorry, gamma W. Gamma W is given in the question as 10 kilonewton per cubic meter. That's why we use 10 here. So the final answer, the initial stress would be 68 kilopascal, right? And then we have to use the 2 to 1 stress method, right? In 2 to 1 method, if foundation load in 150 is applied over there, so it will be distributed 2 to 1. Where vertically, if you go 2 meters down, horizontally you have to go 1 meter. So the total depth is 3 meter, means the horizontal distance is here 1.5 meter. Okay. Here also you will be having 1.5 meter. Okay. So totally it will be 3 meter. So 10 plus 3 meter in each direction, right? 10 plus 3 meter. That's why 10 plus 3 plus into 10 plus 3. Here, this is the contact pressure, 150. It should be multiplied by the total area, contact area, 10 by 10. so that it will be a point load now. A point load, then it will be divided by the distributed area. Totally it will be 88 kilopascal. Now what's the problem here? You can see sigma dash C is 80 kilopascal. Now what is the initial stress? 68. Can you remember the graph? It will be somewhat like this. Here you can see this is the pre-consolidation pressure. So it is in the question, it is given as 80. Now this is equal to 80. Okay. In our initial stage, the stress is 68. It is somewhere here. 68. So due to the foundation, the loading will be increased by 88.8 kilopascal. So the final pressure would be 158, 56. So it will be somewhere here. You can see. So both over consolidation situation and the normally consolidation situation is applicable for clay 1. That's why here it is there, no? Recompression curve and this compression curve, it is available for 1 and 2 situations, right? So that's why we have to use both situations in this equation. In this first situation, this will be the recompression CR value, recompression index. It is given in the question as 0.05. 0.05. That's why it is mentioned as 0.05. Initial void ratio, the thickness of the clay layer, it is 6 meter. And then here, this would be the initial stress. This would be the final stress. So under the over consolidation situation, this final stress would be, this is this over consolidation branch, no? In this branch, the final stress would be 80. That's why it is applied 80 here. Okay. This one will be the initial condition. Initial condition is 68. Here, 68, right? How about this situation? This is 156, no? 6.8. Okay. So in this situation, here again, you have compression index. It is given in the question 0.15 here, 0.15. That's why you apply 0.15 here. And the initial void ratio is given in the question. This is the thickness. And then this is the final stress 156.8. And this is the initial stress of the normally consolidated situation. So initial stress of the normally consolidation situation is PC. This is where the normally consolidation take place, begins. So here it will be 80. The final stress would be 156.8. That's why here 156.8, here 80. Hope it is clear to you. So total settlement would be 15.8 centimeter, right? Similarly, you can check for clay number 2. First, you have to go for the initial effective stress burden. It has been calculated as 128. Stress distribution has been coming as 41.6. Now, the final stress is given as this. So, if you see this condition for clay number 2, what happened? Pre-consolidation pressure for clay number 2 is 200. Means අතීතේ ඉඳන් ගත්තහම එයා 200ක් කලින් හිස්ට්‍රියේ ප්‍රෙෂරයිස් වෙලා තියෙනවා. දැන් ඔන්න pre-consolidation pressure එක 200යි. What happened now? The initial of effective stress is 128, somewhere here. 120 means now it is at over consolidated clay stage. The final stress is 41, so that 41 plus 128, totally it will be 169.6. Still it is at this stage, means you will be still at over consolidated stage. So the equation you have to use is only this situation. You can see clear indication is there, so that you have to use recompression index, initial void ratio, thickness, final stress is this one, initial stress is 128, so total settlement is 1.4. So final settlement from clay number 1 and clay number 2 is 15.1, 15.9 for clay number 1, 1.4 for clay number 2. You can see the extent I am asking from your question paper is this much. So you have to understand what is pre-consolidation pressure, what is the initial stress, what is the final stress. So how to understand which stage your clay is. Maybe normally consolidated stage, maybe over consolidated stage, maybe normal consolidated stage, maybe over consolidated. Depending on the situation, you have to apply your correct formula and calculate the settlement. That's what you have to do, right? Okay. So with that, I feel I have given you sufficient knowledge to answer the exam paper. This presentation, it is already there in your LMS model, so that you can go there and download and see these questions. So today I will wind up the session, Madhushani. Now it is to 8:40. So I will wind up the session. So if you have any question, you can ask now. Madhushani, if you have any question, you can ask now. If not, we will wind up the session.
No
So there are
question,
many
sir.
questions. No questions?
Yeah.
Okay, that's good. Hope everything is clear to you. So anyway, Madhushani, there are many questions available in this presentation. When you have time, I know you all are busy with your day-to-day work and your, occupation and everything, I understand. But it's better if you refer to these questions, especially the question I discussed with you before you come to the exam. Try to work this question, right? So it's better for you, because similar like this question will be there. I will not say which stage is clay is, whether it is normally consolidated or I will not say in the question. So you will have to determine whether this clay is over consolidated or normally consolidated. Okay. So depending on that, to develop your theories, and then you have to evaluate the final settlement. That's what it is expected from your exam paper, right? So with that short note, we will wind up the session, Madhushani. So we will meet tomorrow as usual around 2 p.m. And after that, we will be continuing some of the major things. Tomorrow, I am expecting to uh, discuss some additional things with additional hours. So we will meet tomorrow, will be our last lecture. So we will discuss some of the exam paper considerations, and also we will discuss some of the model papers tomorrow. So share the information with the others, ask them to join tomorrow. So we will wind up the session. Thank you for joining, Madhushani. Good night.
Thank you, sir. Good night.
Good night.